All right, welcome to The Explainer. Today, we're going to trace the incredible journey of natural language processing. We're going right from scratch with the early, super rigid rules all the way to the expert, flexible AI that we use every single day.
Okay, so let's just dive right in. How does a machine actually get what you're saying? I mean, it's a question that has kept computer scientists up at night for decades. Because, let's be real, human language is messy, it's nuanced, and for a machine that thinks in pure logic, that's a huge, huge problem.
Okay, so take a simple sentence like this one. Am I saying I used a telescope to see the man, or is the man I saw holding a telescope? Right there, that's ambiguity. And that simple little problem, it is the absolute core challenge of getting a machine to understand us.
So, how did the pioneers even start to tackle this? Well, the very first attempts focused on creating this super rigid blueprint for language, kind of like how an architect has a blueprint for a building. The thinking was, hey, if we can just define all the rules, we can understand any sentence.
And the absolute cornerstone of this blueprint approach, it was a process called parsing. You probably remember this from grade school, right? Diagramming sentences. It's all about breaking a sentence down into its grammatical building blocks, the nouns, the verbs, all that stuff, to see exactly how it's put together. So here's how it would work in practice. The machine starts at the top, S for sentence. Then it breaks it down, piece by piece, just following its rulebook. Okay, a sentence is a noun phrase plus a verb phrase. Then it breaks those down further. If it gets to the end and all the pieces fit perfectly into the blueprint, bam! The machine says, yep, this is a valid, grammatically correct sentence.
And the engine driving this whole process? It's usually something called a context-free grammar, or CFG. Think of it as the master rulebook for how sentences are built. Now, the key word here is context-free. It means a rule is a rule, period. It doesn't care what the other words are or what the sentence is about. And that's great for something clean and logical like a programming language. But for our messy human language, yeah, that's a major blind spot.
And this brings us to the first huge wall they hit. A machine using these rules could look at a sentence and tell you, yep, that sentence is built correctly. But it had absolutely, positively zero idea what the sentence actually meant. It could check the grammar, but it couldn't grasp the meaning.
And this slide really nails the huge shift in thinking that had to happen next. The focus had to move away from just the structure, the syntax, and toward understanding the actual meaning, the semantics. It wasn't enough to know the parts of a sentence. We needed to know the roles they played.
And this is where thinkers like Charles Fillmore came in, with ideas like case grammar. The whole idea was to stop just labeling parts of speech and start asking, the important questions. Who did the thing? What did they do it to? And what tool did they use to do it? So now with a sentence like, John opened the door with the key, the machine could finally see the relationships. It knows John is the agent doing the action. The door is the object receiving it, and the key is the instrument being used. I mean, this was a massive, massive leap towards real understanding.
Then you add guys like Roger Schenck, who took it a step further. He had this really cool, kind of radical idea. What if we could boil down all sentences to a small set of primitive, universal actions? The idea was, no matter how you say something, if it means the same thing, the machine should represent it in the exact same way.
Take this, for example. John gave Mary a book. Mary got a book from John. Totally different words, different sentence structure, right? But the core idea is the same, a transfer of ownership. Schenck called that primitive action a trans. And for the first time, a machine could look past the surface words and see that these two different sentences actually meant the same thing.
But here was the problem, and it was a big one. Trying to manually write down all these complex rules for meaning, it's just impossible. Human language is too vast, too creative. So a totally revolutionary idea started to take hold. What if we stopped telling the machine the rules and instead just let it learn them, just like we do, by observing patterns in tons and tons of data?
Look at this phrase. A system based on those strict grammar rules would just throw an error. It's not a real sentence. But you know exactly what it means, right? And so do modern AIs. Why? Because they threw out the rulebook.
So instead of grammar, these new systems are all about probability and patterns. They've seen billions of examples from the internet. They don't know that book is a verb here. They just know that the words book,
flight, and deli have a super high statistical chance of appearing together when someone's trying to make a travel request. It's about probability, not rules. And that was the game changer.
And this fundamental shift from rules to probability absolutely revolutionized fields like machine translation. We went from those clunky, pretty literal rule-based translations to the much more fluid, much more accurate neural models that we all rely on today.
So here's the thing. This powerful new ability to learn from data didn't just solve the understanding problem. It also unlocked the other half of the conversation, being able to generate intelligent language. So not just listening, but talking back.
And that brings us to the two sides of the modern AI coin, NLU and NLG. Think of it this way. Natural language understanding, or NLU, is the ear. Its job is to figure out, what is the user trying to say? And natural language generation, or NLG, is the mouth. It asks, okay, now how do I respond in a way that sounds human? You put those two together, and that's how you get the magic of something like ChatGPT or the voice assistant on your phone.
So when you look at this whole journey, from scratch to the expert systems we have now, it's really a story of evolving our entire approach. We started in the 60s with rigid, logical blueprints. Then in the 70s, we realized we needed meaning. But that was too hard to scale by hand, so in the 90s, we shifted to learning from data. And that, of course, led directly to today's neural revolution. Each step got us closer not to a perfect set of rules, but to how humans actually use language.
Which leaves us with one last kind of mind-bending thought. We have spent all these decades teaching machines to speak our language. What happens next when they start creating their own? We've successfully recreated our most human trait in silicon. The next chapter in this story? Well, that's the one we're all about to write together. Thanks for watching.